Hello everyone, I am Luca Sani. I am a catchpoint engineer working on BGP monitoring. And now I am going to present you a work done together with my colleague Alessandro Improta. Since this is the first NANOG of the year, we thought that could have been nice to give a summary of what happened from a BGP security perspective last year. So it is well known that BGP is not immune to security problems, in particular to routing incidents. We can have an estimated number of the incidents that happened during time by looking at the BGP stream web page. This page reports the incidents perceived by BGP stream and classifies them on the basis of their nature. In particular, we are interested in hijacks and leaks. As you can see from these numbers, during each month of last year, hundreds of incidents happened. In particular, there is a peak in June of last year where also the leak affecting Cloudflare happened. So the main problem is that BGP wasn't designed with security in mind. By looking, for example, at public interviews released by BGP authors, we can say that when BGP was designed, security wasn't even on the table. And the main goal was just to get the internet to work. So this is why BGP lacks of an intrinsic mechanism to secure packets, and this is why it is prone to misconfigurations and attacks, in particular hijacks and leaks. An hijack occurs when an autonomous system claims to be the origin for a portion of IP space that actually has been allocated to another one. For example, in this slide, you can see that Autonomous System 5 claims to be the origin for the prefix P, which actually has been allocated to Autonomous System 4. Autonomous System 5 sends this BGP message to its BGP neighbors, which may or may not accept the announcement. For the sake of the example, suppose that Autonomous System 3 accepts the announcement and propagates this information to its neighbors. And again, suppose that AS1 accepts the announcement. The consequence is that all the traffic from AS1 and AS3 directed to P will be actually received by Autonomous System 5 instead of Autonomous System 4. At this point, the destiny of the traffic depends on the intention of AS5. If the hijack was created by mistake, probably the traffic will be just dropped, causing a denial of the services running on prefix P. On the other hand, if the attack was done on purpose, AS5 could inspect the traffic, or even worse, could try to impersonate the services running on P, trying, for example, to steal login credentials from end users. This kind of hijack is often called mis-origin hijack because it is clear from the autonomous system path that the most right autonomous system number is not the expected one. More complicated versions of hijacks exist. For example, one version is called AS path forgery, where the attacker on purpose includes into the autonomous system path as the most right autonomous system number, the number of the expected origin, with the aim to make the attack more difficult to be detected by BGP monitoring platforms. The other class of incidents we are interested on is the class of route leaks. A route leak can be formally defined as the propagation of a BGP announcement beyond its intended scope. The scope can be defined using the BGP import and export policies, which govern the set of routes that two autonomous systems exchange on a BGP session. Very roughly, these policies can be classified into main categories: customer provider and peer-to-peer. In a customer provider policy, the customer announces to the provider the routes to reach its networks and the networks of its customers, while the provider announces to the customer the routes to reach all the internet networks. On the other hand, in a peer-to-peer policy, the two autonomous systems exchange routes to reach its respective networks and the networks of its respective customers. So a leak happens when an autonomous system propagates a route learned from a peer or a provider to another peer or a provider. For example, in this slide, suppose that Autonomous System 5 is customer of Autonomous System 4 and peer of Autonomous System 3. AS4 announces to AS5 the reachability of prefix P, and by mistake, AS5 propagates this information to AS3. If AS3 accepts this route, all the traffic from AS3 directed to P will pass through Autonomous System 5. So de facto, Autonomous System 5 will be a transit between a peer and a provider for that kind of traffic. The main consequence of a leak usually is performance degradation, because the autonomous system causing the leak will have to handle an unexpected amount of traffic. And its network may be under-provisioned in order to handle this kind of traffic. A leak could also be done intentionally with the purpose of stealing the traffic that anyway will be directed to the proper destination. Now we are going to analyze 3 relevant cases that happened during last year. The first case is a leak involving a Swiss data center colocation company named SafeHost. This leak had a huge impact in the news, mainly because it involved also directly China Telecom. So all the news highlighted the fact that a lot of internet traffic was redirected through China. So what happened is that in the morning of the 6th of June of last year, the Swiss autonomous system SafeHost started to announce to its provider, China Telecom, more than 40,000 routes learned from other peers and providers. Those routes involved both prefixes already present in the routing table, as well as prefixes not present. In this case, we observed both more and less specific prefixes. China Telecom, in turn, accepted all these routes and propagated them to its neighbors, de facto contributing to spread the leak on a global scale. The leak also reached autonomous systems connected to public route collectors of route user RIS. And in the bottom of the slide, for example, you can see a few examples of leaked routes. You can notice the presence of the autonomous system of China Telecom 4134 and the presence of the autonomous system of SafeHost 21217. Also, you can notice the presence of prepending, as if SafeHost didn't want to use the link with China Telecom for those routes. So we tried to analyze the global impact of the leak by analyzing the amount of peers connected to a route collector that received at least one leaked route. To perform this analysis, we downloaded all the available update messages from route views and RIPE-RIS archives. And as you can see from the pie in the left of the slide, almost all peers connected to a route collector received at least one leaked route. To be more precise, we have to say that we considered only the peers sharing a full routing table with the collectors. From another perspective, by looking at the histograms in the right side of the slide, we can say that the leak was spread on a global scale without saving any internet region. To claim that, we classified the peers receiving the leaked routes on the basis of their registry of membership. The registry of membership can be considered a very, very rough indication of the location of a peer. So it is true that almost all peers connected to a route collector received at least one leaked route, but it is not true that all peers received the same amount of leaked routes. To capture this concept, we plot the distribution of the number of origins on the left and the number of subnets on the right that each peer perceived as involved in a leaked route. As you can see from the distribution, for example, we can say that only the 20% of peers received leaked routes involving more than 100 different origins. Of course, the collector peers directly connected to China Telecom were the peers announcing to the collector the highest number of leaked routes. For example, there were one peer which announced to the public route collectors routes involving more than 3,000 different origins and 25,000 different subnets. This leak lasted globally almost 4 hours, and during these 4 hours, more than 6,000 different origins were affected. Here you have the distribution of the evolution of the number of origins affected by the leak during time. As you can see, there are several peaks. For example, there is one peak around 10:40 a.m., where more than 2,000 different origins were affected at the same time. Among those origins, there were popular services like WhatsApp and Microsoft, but also internet service providers, transit providers, banks, and all kinds of autonomous systems participating to the internet. Another case that we investigated involved an autonomous system located in the island of Taiwan. This incident didn't have a huge impact in the news like the previous one. However, it is interesting to analyze because it is a perfect example of origin hijack. So the scenario is the following. There is the Taiwan Network Information Center, which runs the network 101.101.101/24, on which it is run a public DNS project called Quad 101. At some point during the 8th of May of last year, a Brazilian autonomous system called Fibra Plus started to claim to be the legitimate origin for that network and propagated this announcement to its provider, Claro Brasil. Claro Brasil accepted this information and propagated this information to its neighbors. So Claro Brasil is a medium-large internet service provider in Brazil, so de facto contributed to spread the hijack on a global scale. In the bottom of the slide, you can see a few examples of the hijacked routes, where you can clearly see that the most right autonomous system is the autonomous system of Fibra Plus. Differently from the previous case, which was a leak, in this case, this network is announced at the same time between two different autonomous systems. In Asia is announced by Taiwan Network Information Center, and in South America is announced by Fibra Plus. So if we analyze how this hijack spread globally, we can see that those autonomous systems closer to the hijacker network, so those autonomous systems located in LACNIC, tend to use the hijacked route. So you see that all the peers in LACNIC basically accepted this route, while those autonomous systems closer to the Taiwan Network Information Center tend to not use the hijacked route, as you can see from the IPNIC histogram. The last case that we analyzed is the case that was previously presented by Mr. Levy, so I won't go in much details, but I want to give you a view from what can be seen from publicly available data. So this leak had a huge impact in the news, mainly because it involved the famous autonomous systems like Cloudflare, but also Facebook and Amazon, and also because Verizon was blamed for spreading the leak. So very briefly, what happened is that the autonomous system of ATI propagated to its provider Verizon thousands of routes learned from another provider, DQA Communications. To be honest, DQA Communication wasn't supposed to generate those routes. So this is a perfect example of provider-to-provider leak. In turn, Verizon accepted all these routes and propagated them to its neighbors. Among them, there were the Verizon customers, there were Tier 1 autonomous systems that accepted the routes, and also other Tier 1 networks that dropped them because they had in place strong filtering mechanisms like RPKI or peer lock. So on a global scale, the leak was perceived by almost all autonomous systems connected to a route collector, with some exception in the ARIN region. Those exceptions include autonomous systems that dropped the routes thanks to filtering mechanisms, like, for example, AT&T and Entity, and also their respective customers that were protected from the leak. Again, so it is true that almost all peers connected to a route collector received at least one leaked route, but it is also true that not all peers received all the same amount of leaked routes. In particular, in this case, you can see that Verizon, which is also connected to public route collectors, received and announced to the route collector leaked routes involving more than 4,000 different origins and more than 65,000 different subnets. The leak lasted almost 2 hours, and during these 2 hours, all these origins were affected, and among them there were, again, famous autonomous systems like Facebook, Cloudflare, T-Mobile, Bloomberg, also American banks, and so on and so forth. So every kind of internet player was affected. So these were just 3 relevant cases that we analyzed, but many, many more happened during last year. Again, by looking at BGP stream numbers, we can say that last year, more than 600 autonomous systems were victim of an hijack, and more than 800 autonomous systems were victim of a leak. We can have a better understanding about the nature of this autonomous system, for example, if we try to rank them on the basis of their size. To do that, we used the methodology provided by CADA, which is called AS-Rank. This methodology allows you to have an estimation of the size of an autonomous system on the basis of their customer cone size. So as you can see from these 2 pies, almost all kinds of autonomous systems were affected, from smallest one to biggest one. So no autonomous system is safe from leaks and hijack. Also, these numbers are very likely to be underestimated, mainly because the number of autonomous systems participating to a public route collector is very limited, and also because not all autonomous systems connected to a route collector announce to the collector everything that they receive. For example, let's consider this scenario where the route collector R is connected to autonomous system E, and let's suppose that autonomous system C generates a leak. The leaked route could reach autonomous system E, and now suppose that E has in place strong filtering mechanisms, for example, RPKI validation, so it drops the route. In this case, the route collector R will never be able to see the leaked route, even if the leak actually happened. To have a proof of that, we tried to plot the distribution of the number of BGP stream peers that detected the reported hijack and leaks. As you can see, not all peers perceived all the events. For example, by looking at the route leaks, we can say that only the 40% of leaks were perceived by more than 20 BGP stream peers. So what can we do about it, and what have been done about it? Since BGP lacks of an intrinsic mechanism to secure packets, a lot of mechanisms have been proposed during time. The most famous and used one is RPKI, as you know. So RPKI is a powerful mechanism, and everyone should sign their prefixes. However, it is also well known that it is not enough to drop all the invalid announcements. For example, as we are going to see in a slide, it can't drop some kind of BGP leaks and intentional attacks like ASPAT forgery or subprefix hijacks. So let's consider again the leak scenario, where Autonomous System 4 announces to 5 the reachability of P, and suppose that Autonomous System 4 signed in the RPKI database that it is the legitimate origin to announce prefix P. Now let's suppose that this announcement is propagated by Autonomous System 5 to Autonomous System 3, and then to Autonomous System 1. And let's say that in this scenario, Autonomous System 1 is the autonomous system performing RPKI validation. So upon receiving the BGP announcement, Autonomous System 1 will look if the most right autonomous system in the path is the expected origin for the legitimate origin for the prefix P. And the check in the RPKI database will return valid because prefix P has been registered by Autonomous System 4. So for this reason, a lot of other mechanisms have been proposed during time. For example, BGP-SEC, where BGP packets will be cryptographically signed. And also a lot of other mechanisms are in discussion in IETF in order to detect and drop invalid paths and leaks. So I just want to conclude this presentation by saying that despite all these mechanisms are in place and new mechanisms will be proposed, BGP monitoring can be still useful in order to detect and to react as soon as possible to invalid announcements that escape these mechanisms. So that's all. If you have questions, I am happy to take that.